Okay, I am very happy to begin this small workshop on black hole analogy. I bring the greeting from our chancellor, our head of the department. They cannot be here clearly because there are a lot of very important things to do, very boring also, I guess. And I thank all guests that come from far, like Stefan, Karen. Your first name is Jeff. Great. Jeff, for being Francesco, for being here in Urbino. Many of you is not the first time. Stefan and Karen were here not a lot of time ago. So I am very happy that they are again here in Urbino. They found the experience not so bad, I think. And the topic is incredibly wonderful. It is wonderful that here we have experimental physicist, philosopher, physicist all together that will speak about this incredible topic that is very, very exciting, like the problem of analogical reasoning in black hole physics. And I thank Giovanni, that was a deus ex machina of all organization. He make all possible. I thank him a lot for spending a lot of time in the organization of this workshop. And I think that we can begin to speak together about this incredible topic. Thank you very much for being here.
But I want to thank Giovanni Macchia and Vincenzo Fano for organizing the workshop, even if I couldn't be of much help this time. So what I want to do before the talks begin is to say a few words about the project that is funding this workshop. It's a project that is titled Analogical Reasoning in Contemporary Physical Theories, and it has myself and Vincenzo as PIs. In fact, the project is led by the two teams, one the Polytechnico in Milan and the other one in Urbino. And the purpose of the project is to explore the condition of plausibility of analogical inferences in physics. And we focus in particular on two case studies from contemporary physics. The use of analogy in subatomic physics, like for the Higgs boson, and that's the task of the Milan research unit. And also the other case study is the one that will be addressed today and tomorrow in Urbino. In fact, it's the focus of the Urbino piece of research, and it's on analogical experiments in black hole physics. The project also has a pedagogical component, so we look at the use of analogies in teaching physics, especially in high school. And so that's the project in a nutshell. The project is about to end. So this fall is going to be the last couple of months of the project. And it started 2 years ago. In fact, we had a conference in Milan last November, and now this last workshop in Urbino. So as a last thing, I just want to list all the people that are part of the project beside myself, Vincenzo Fano. We have Giovanni Macchia, Gino Tarozzi in Urbino. We have Antoine Brandelet, Anna Paola Ginammi, myself, and Domenico Brunetto in Milan. And I should also say Francesco Nappo is not officially in the team, but he was already working in my department and being an expert on analogical reasoning. It was a big asset for the successful completion of the project. So again, I'm sorry I won't be there. I'm not there, but I will participate online at the rest of the conference. Thanks again to all of you for being there.
Thank you, Giovanni. I think that we can start. The first speaker today is Jeff Steinhauer from Israel Institute of Technology, and they will speak about spontaneous Hawking radiation in sonic black hole.
I'd like to thank the organizers for inviting me to this very interesting conference, combination of physics and philosophy. And I'm very much looking forward to hearing all the other talks. And I'm going to be discussing mostly on the physics side, our observation of spontaneous Hawking radiation in a sonic black hole. And this work builds on a rich theoretical history, beginning with Jacob Bekenstein, who pointed out that a black hole has entropy and temperature. It's not just completely defined by just a few macroscopic parameters. It also has entropy and temperature. And Hawking then found that a black hole should radiate at the very temperature predicted by Bekenstein. And in making this prediction, he combined general relativity with quantum field theory. So his prediction is considered a first step towards achieving a theory of quantum gravity. And the equation that he came up with for the Hawking temperature is the temperature is proportional to the surface gravity over the speed of light. Now, the problem with observing Hawking radiation from a real black hole is that the Hawking temperature should be extremely low. So for a black hole with a mass of a few solar masses, the Hawking temperature should be less than a microkelvin. So it should be totally overpowered by other sources of radiation, such as the cosmic microwave background. But perhaps one could find very small black holes, which would have a higher Hawking temperature, because the characteristic wavelength of Hawking radiation is on the order of the diameter of the black hole. So if you have a smaller black hole, it would have a longer wavelength, a shorter wavelength of Hawking radiation, which would be a higher temperature. So perhaps tiny primordial black holes were created in the early universe, as described in 1976, but nobody's seen such things. No one's detected primordial black holes yet. But perhaps black holes might be detected at the LHC, at the Large Hadron Collider. And I'll discuss in a moment various searches for black holes at the LHC. Now, semi-classical black holes. So this is, in order to understand these searches for black holes, we should understand semi-classical black holes and Hawking radiation just a little bit. So if here's a black hole, here's its event horizon. It should emit Hawking radiation, which are some positive energy particles. And for each Hawking particle, there should be a partner particle falling into the black hole. And the partner particle inside the black hole, because it's inside the black hole, has negative energy. And so you have zero total energy for the pair. And so this radiation can come from nothing, from the vacuum at the event horizon. And Hawking predicted a thermal distribution of pairs. So it's not just one frequency, it's a distribution of frequencies. And you should have energies, and it should include all the standard model particles. So that's the semi-classical prediction of Hawking. So now in these black hole searches at the LHC, some of these searches are for semi-classical black holes, as we just described. So they're looking for a thermal emission of all the standard model particles should be coming from these black holes. Another type of search would be quantum black holes. Quantum black holes are so small, a quantum black hole, that it decays into just 2 jet final states, meaning this black hole is split into 2 particles. That's all it is. It's so small, it splits into 2 fundamental particles. And so these black holes are not semi-classical. You can't think of them as somehow emitting a thermal distribution of all the standard model particles. They just split into 2 particles and that's it, they're done. So there have been many semi-classical black hole searches over the years and also quantum black hole searches, but they haven't found anything yet. I guess the idea, if we're on this, well, since we're on the subject, the idea is that in certain theories with extra dimensions, the Planck mass should be much lower, as I understand it. And if the Planck mass is much lower, then you could have black holes produced at the energies of the LHC. So that would be the basis of these observations. So now I'll just discuss a few issues related to black holes. There's the information paradox. And the question is, let's say information were to fall into a black hole, like if you threw a computer into a black hole, where would the information go? What comes out of the black hole is Hawking radiation, and that should be thermal, it should be random, and should have no information. So Hawking had asked, information which crosses the event horizon is irretrievable. The phase of the Hawking radiation cannot be predicted. Thus, there is uncertainty beyond the Heisenberg uncertainty principle, which is in violation of quantum mechanics. So Hawking was really asking what happens to this information. One can particularly see this problem of the information paradox if one considers an evaporating black hole. So the Hawking radiation is coming out of the black hole, which means that the black hole is losing energy there. The negative energy particles falling into the black hole. So the black hole is evaporating, it's losing mass. And it loses more and more mass until the black hole is completely gone. So, and all that's left is Hawking radiation. So what happened to any information? Where did any information go which was used to create the black hole or that fell into the black hole? And the answer may lie in quantum gravity. If one looks in the literature, there are countless articles providing solutions to the information paradox. And often the solution is lies in quantum gravity in these articles. Another issue is Planck scale physics. So if one looks at the Hawking radiation reaching us on Earth, it'll be coming with some finite wavelength, some finite temperature. But if you trace it back to the black hole, there's this blue shifting. The wavelength becomes very, very short and becomes 0 at the horizon, goes to 0. So the wavelength drops below the Planck length scale. And no one knows what the physics is for wavelengths shorter than the Planck length. So it calls Hawking's calculation into question because his calculation seemed to be based on these Planck length scales. So at that time, his prediction was controversial for this reason. And Hawking, and this seemed to inspire Bill Unruh to come up with the idea of sonic black holes, analog black holes. He pointed out in his paper in 1981, black hole evaporation is one of the most surprising discoveries of the past 10 years. And that seemed to inspire him to write his paper. And he came up with the same equation for the Hawking temperature in a sonic black hole, where G is now the analog of the surface gravity and C is the speed of sound. So there have been many systems proposed as possible sonic black holes. Bose-Einstein condensates is one very popular one. There are many, many articles on this subject. Also, superfluid helium-3 is a possible platform, as is an electromagnetic waveguide, ultra-cold fermions, rings of trapped ions, superconducting circuits, light in nonlinear liquids, exciton polariton condensates, magnons in a magnetic wire, while semi-metals. And now on the experimental side, my group has been studying this problem since 2010. I became interested in this. I had read some theoretical articles on the subject, and I was thinking about how to produce a sonic black hole. And I happened to stumble upon a solution while working on a different experiment. So I just dropped my other experiments as soon as possible and have been working on pretty much only on this ever since. So we made a systematic study. We started out by learning how to produce sonic black holes. In other words, it means that we have to get this very ultra-cold gas to flow faster than the speed of sound. I'll discuss that more a little bit later. And we then just learned how to study very small quantities of phonons, since for us, the Hawking radiation is phonons. And then we eventually managed to observe the stimulated Hawking radiation, and then we went on to observing the quantum spontaneous Hawking radiation, which is what I'll be discussing today. Another experimental subject which is under experimental study is surface waves in water. On the surface of water, one can observe the classical stimulated effect. One can send waves of water, and that hits the horizon and stimulates pairs of water waves. And the reason you can't see the quantum spontaneous effect is because the water is too warm. I heard Bill Unruh say in one of his talks, Bill Unruh being the guy who had invented the analog black hole, he said if he could cool his water tank down to picokelvin temperatures, that he could see the spontaneous Hawking radiation. So another area of active study is nonlinear optical fibers. And they've seen so far the stimulated classical effect of Hawking radiation. Exciton polariton condensates, I believe they're still working on trying to see the Hawking radiation in this system. So here's a picture of our sonic black hole. So here it is, and this is what you're seeing there is a picture of 8,000 atoms approximately. And they're confined to a long volume, like a pencil-like volume. And where it's white, that means more atoms, and there are fewer over here. This is a Bose-Einstein condensate. It's very, very cold. It's sub-nanokelvin temperatures, so it's even very cold for a Bose-Einstein condensate. And it's a gas, which is a gas of rubidium atoms. And it's flowing from left to right. So in this region here, it's flowing slowly. It's flowing slower than the speed of sound. Whereas over here, where there are fewer atoms, it's flowing faster than the speed of sound. So if you consider a sound wave, a phonon, inside in the supersonic region, it going against the flow, it can't go forward against the flow. Meaning in the reference frame moving with the fluid, it's going against the flow, but the fluid is moving faster than the speed of sound. So in the laboratory frame, this phonon is going backwards. So it's unable to reach this point over here. So this is like the horizon of so it's similar to a photon stuck inside of a black hole. This phonon can't reach the horizon. So, but over here on this side, the flow here is slower than the speed of sound. So over here, a phonon can go forward against the flow. So one can picture, this phonon on this side, the one in the supersonic side, has so much Doppler shift that it has negative frequency, meaning it's going the wrong way. It's like frequency is how, if you put your hand here, how many wavelengths pass your hand per unit time. That's the frequency. If the fluid's going that way, the wave is going the wrong way. A negative number of wavelengths past your hand. The wavelengths are going the other way. So you have a negative frequency. And now if you ask, what is the energy of a phonon, like a photon? It's h bar omega. So it's proportional to the frequency. So if the frequency is negative, the energy of the phonon is negative. The energy of the quasi-particle, as it's called, is negative. So whereas on this side, in the Hawking radiation side, outside the sonic black hole, the energy is positive of these phonons. So you could have a pair which have zero energy, and this is the Hawking radiation. So I'd like to now tell a few details of how we create this sonic black hole. So it was confined in this long, thin volume. That's because it's confined at the focus of a laser beam. So here's a laser beam, it's focused, and there are atoms trapped by the light. The light traps them in this long, at the focus of the laser beam. And this is the vacuum chamber, this rectangular region. So this is like 1 centimeter large. And from below, there's a lens, which is, it's like a microscope objective. And it's, so we can see these particles and make the picture that I just showed you in the previous slide. And so it's imaged onto a camera somewhere. And there's also a coil, a magnetic coil, an anti-gravity coil, because this laser beam is too weak to support the atoms against gravity, because we get a larger signal for the Hawking radiation when the density is low. So, we don't hold these atoms very tightly. We don't want to squeeze them too much and increase their density. So the laser can't counteract gravity, so we have this magnetic field gradient, which holds the atoms against gravity. Then there's also an imaging laser which comes from above. In order to see these atoms, we need some kind of source of light. So there's this imaging laser, and the atoms put a phase shift on the laser beam, meaning the atoms have an index of refraction, and so they cause a phase shift on the imaging laser, and then we have a reference laser, you can say, and it gets imaged on, and that appears on the camera. That's how we get an image like this one. We're seeing the phase shift put on the laser beam by the atoms. So here's the picture of the vacuum chamber. And here, and so what we were looking at here's the laser beam which traps the atoms here in the vacuum chamber. And you can see that the laser beams are going through these paper tubes, these paper air tubes. And the reason that there are all these paper tubes is so the air in the room doesn't move the laser beams. The cloud of atoms is so cold, like sub-nanokelvin temperature, as I mentioned, that if the laser, just due to the motion of the air in the room, if it moves a little bit, it will heat up the atoms a lot. So, but these paper tubes do the job of preventing that. And now I mentioned that it's flowing, the condensate is flowing slowly here and fast over there. That's because there's a potential step, and the atoms are flowing slowly. They go over this step, and they're accelerated to supersonic speeds. Now, this step is created by another laser beam. So here are the atoms. There's this laser beam, which is like a laser beam coming at us, an elliptical shaped laser beam, and it's been cut in halves by a knife edge somewhere in the imaging system. So it's blocked. Half the laser beam is blocked. So there's this sharp transition from light to dark. So when the atoms come, and this laser beam is blue, which implies that it provides a repulsive potential for the atoms. So when the atoms are inside the laser beam, if they come out of the laser beam, they lose that repulsive energy, and it's like they went over a step, and they get accelerated. So in other words, the potential energy that they have inside the laser beam gets converted into kinetic energy when they come out of the laser beam. So that's how we make this step potential. Now, this step potential, this laser beam, is moved slowly through the condensate, slower than the speed of sound. And the reason we do that is we can see if we go into the reference frame where the laser beam is not moving, it's as if the atoms are moving to the right. It's really the laser beam that's moving, but it doesn't matter. So it's like the atoms are moving to the right. So they move to the right, they flow over the step and are accelerated to supersonic speeds. Now, this is just some lenses. Here's the laser beam coming in, the repulsive laser beam. It goes through some lenses and is focused onto the atoms. And so that comes in here from this side. So here's where the laser beam for the step potential comes in. And somewhere else in the imaging system, there's a mirror, a rotating mirror, which is what slowly moves the laser beam along the atoms. As we said, the laser beam moves and it's as if the atoms are moving and they flow over the potential step. We also, so we're going to repeat this when I showed you this picture of this sonic black hole. That was one realization of the experiment. In order to see the Hawking radiation, we're going to repeat that about 7,000 times, which takes 9 days. So in order to gather enough data to see the very weak Hawking radiation. So during that time, we have to keep the system very stable for those 9 days. And so we want to make sure that the condensate doesn't move slightly along its axis, that the cloud of atoms don't move along the axis. So we turn off the step, and here's what it looks like with no step. And we keep it centered in the picture by adjusting some magnetic field. So we take a few of these images, every few hundred images, we take a few with no step. So here's what the system looks like from far away. So here, what we saw was over here. And so here's a table, this optical table, and there's all this optics. This is for the first stage of the cooling, is laser cooling. In order to cool the atoms to the sub-nanokelvin temperatures, the first stage is with lasers. So you have atoms, any direction the atom moves, there's a laser which stops it. So if it goes this way, a laser stops it from here. If it goes that way, a laser stops it from there, and all the different directions. So, and so the atoms move very slowly, and that means that they're becoming cold. So this is, you see a lot of optics for that. And here's another view of the vacuum chamber. What we saw was over here, and again, you can see these mirrors, big mirrors which direct the light into the vacuum chamber. And just another view of the vacuum chamber. And here's a lower view. With what we saw was up here. This is a lower level of the vacuum chamber, and this is a lot of the imaging optics. And you can see these air tubes that I had mentioned. And here, this is just another table with some lasers on it, the lasers are brought by optical fibers over to the table that I showed you before. Now, so getting back to Hawking radiation, so we would like to determine what Hawking temperature we expect. What is the predicted Hawking temperature? Then we'll discuss observing the Hawking radiation, and we'll check if the temperature is the predicted temperature. So the predicted temperature is given by this formula, the surface gravity over the speed of sound. So the effective surface gravity is given by the derivative, the gradient of the flow velocity and the speed of sound. V is the flow velocity. And C, that should be Okay, speed of sound, cs dx. So, and these should be evaluated, these derivatives should be evaluated at the horizon. So in other words, here's the sonic black hole. Right here at the horizon, the flow velocity and the speed of sound are changing. We said that the flow velocity goes from being below the speed of sound to being above the speed of sound. So there's some derivative in the flow velocity. And we see that the density is high here and low there. So there's a change in the density, there's a change in the speed of sound also. So we should evaluate these derivatives. So we can integrate this picture vertically to make like a one-dimensional plot of the density, like this. This is at various times, these various plots. But so anyway, so this is the density as a function of position. And we want to take the derivatives here at the very steep part. And we should now, in order to get the derivative of one of the derivatives we want is the speed of sound. That we can get just because we can convert density to speed of sound. The higher the density, the higher the speed of sound. And for our Bose-Einstein condensate, we can make that conversion. So we can get this derivative. The flow velocity, in order to get the flow velocity, what we're going to do is we're going to assume a constant current. So if the current is constant, that means that where the flow velocity is high, the density has to be low. The product of density times flow velocity has to be a constant. So we can convert the derivative of the flow velocity to a derivative of the density, as in this expression here. So from the density, we can get both this derivative of the speed of sound and the derivative of the velocity and compute the Hawking temperature. Now, if we do that, we get these blue circles as a function of time. This is a function of time after the creation of the horizon. And this is the log of the Hawking temperature. And these blue circles, it's pretty much constant, the Hawking temperature, the predicted Hawking temperature, until the latest times when it goes down a bit. This is very different from a real black hole, where a real black hole might evaporate and it would get smaller and the Hawking temperature would go up as it got smaller. But here it stays constant and then at the end it goes down. So now that's the predicted Hawking temperature. Now we would like to observe the Hawking radiation and see if the observed Hawking temperature agrees with that predicted Hawking temperature. So in order to observe the Hawking radiation, we follow the suggestion in the literature and look at the correlation function. I'll tell you what that means. So here's the sonic black hole. We integrate it vertically and we get a density profile like this. And we are expecting this point, the horizon, to be emitting pairs of waves. One should go out of the black hole and one should fall into the black hole. So if we look at 2 points, x and x prime, which are equal propagation times from the horizon, we expect to see correlations in the density fluctuations because of the pair of waves that have been emitted. And it doesn't matter if we're 2 points close to the horizon or 2 points far from the horizon, as long as they're equal times from the horizon, we should see correlations. So if one plots the correlation function as a function of x and x prime, as a function of this x and this x prime, we expect a band of points with correlations, like this gray band. And each point on this band is a pair of points, x and x prime, which are equal times from the horizon. So we're going to look for this, and that's how we're going to see Hawking radiation. And now these correlations are negative, meaning if there's a positive fluctuation here in the density, increase in the density here, there's a decrease in the density at x prime. They're negative correlations. And why are they negative? We can understand from this article that the fact that the correlations are negative means that there's positive mutual information between the inside and outside of the black hole. Shows where the information is gone. So now we perform the experiment. We repeat this. We take thousands of these kinds of images. We compute the correlation function. Here's the correlation function, meaning we multiply the density fluctuation at x times the density fluctuation at x prime, which gives a negative number, we said. We said they're negative correlations. And we do an ensemble average over thousands of repetitions of the experiment. And here's what we get, where these are all at various times. For most of them, in most of these plots, you can see a band of correlations starting in the middle and going up to the left. And those are the correlations between the Hawking and the partner particles that we were looking for. So that's our observation of Hawking radiation. For all of these plots here, there's required a total of 97,000 repetitions of the experiment, which corresponds to 124 days of continuous measurement. So now let's zoom in. Now, so we see there are these various periods of time. And so let's zoom in on this one, which is labeled spontaneous Hawking radiation. And in here, in all of these, you can see these bands of correlations between the Hawking and partner particles. And now we would like to convert this to a temperature. We'd like to say, okay, we see this Hawking radiation. What Hawking temperature is that? And does it agree with the predicted Hawking temperature that we got from when we measured the derivatives at the horizon? So how do we convert this to a temperature? This is a position space plot. This is x and x prime. So to convert it to a temperature, one can go to K space. One can take the Fourier transform of this somehow. And K space gives you the wavelengths. And so if shorter wavelengths is higher temperature. So that's basically what we do. But I would like to, instead of going through that mathematics, I'd like to just give more of a qualitative explanation, intuitive explanation. So first of all, if this band is deeper, that means more Hawking radiation. The stronger, the clearer it is, that means that there's more. And more Hawking radiation means higher temperature. A warm body radiates more than a colder body. Like the sun radiates a lot more than, say, a person per unit surface area than does a person because of its higher temperature. So, by this idea of how much, so we look at the depth of this feature and this band, and we can convert it to a temperature. And that gives us these green circles. And these green circles agree pretty well with the blue circles during the spontaneous period. So that means that the quantity of Hawking radiation agrees with the predicted Hawking temperature. Another way that we could convert these bands to a temperature is by the width of the band. If the width is narrow, that means short wavelengths, and short wavelengths means high temperatures. So that we can convert the width of the band to a temperature, and we get the red pluses. And they also agree with the blue circles and with the green circles, the width of the band. So from this, we see, first of all, that the Hawking radiation is at the correct temperature, at the predicted Hawking temperature. It's spontaneous, meaning it's quantum, because this predicted quantity of Hawking radiation is for the spontaneous case, for the case that the Hawking radiation is not being stimulated by anything. And we could also see it's thermal in the sense that the height of the spectrum, given by the quantity of Hawking radiation, the green circles, agrees with the width of the spectrum, the red pluses. So we basically see that the Hawking radiation is spontaneous, thermal. It's stationary, meaning it's pretty much constant during this period, the spontaneous period, as should a black body be. Like a black body radiates a stationary spectrum, like a star radiates constantly the same amount of radiation, on the average. So, this really confirms Hawking's calculation. the various aspects. It quantitatively confirms Hawking's prediction. So, but we notice at earlier times, before the spontaneous period, that's what's labeled the ramp-up period. During this ramp-up period, the quantity of Hawking radiation is lower than predicted. So you have this surface gravity, you have a horizon with a surface gravity, but little or no Hawking radiation. So that seems strange. Well, there is this dashed theoretical curve, which seems to agree with the experiment. So what is that dashed theoretical curve? It's the prediction for a real black hole. So we're considering the gravitational collapse of a cloud of dust. So for a real black hole. So if you have 170 solar masses worth of dust, and it collapses by gravity, we could understand by this article, by the Parentani group, they give us the flux of radiation and as a function of time emitted by this collapsing cloud of dust, which is going to form a black hole. We can convert the flux, we could say it's proportional to the Hawking temperature to the 4th power. And so by the Stefan-Boltzmann law, and so we can convert it to a temperature. And when we do that, we get this, the dashed curve, which agrees very nicely with the data. But that might just be a coincidence because I have no reason to think that our sonic black hole should be somehow related to a collapsing cloud of dust. But there is another explanation, which I think is the real explanation for why the Hawking temperature is very low here. It's called gray solitons. So when the horizon is formed, okay, well, it's covered by this thing, but you may probably remember what's over here. It's sort of this gray band. When the horizon is formed, these gray solitons are emitted. These are a type of wave excitation in the Bose-Einstein condensate, and they travel upstream out of the black hole. It's sort of like the black hole is shedding energy. And while it's shedding this energy to form the horizon and go into the stationary configuration, we don't see the Hawking radiation. The Hawking radiation either is not emitted or it's masked by these gray solitons. And we can see the gray solitons in the correlation function. This blob here in the correlation function are the gray solitons, and they move out of the image as we go to later and later times. It's moving down and to the left, this thing, until it's gone. And so while it's still there at early times, the Hawking radiation slowly needs to ramp up. So now at later times, an inner horizon forms. At the end of the spontaneous period, why does the spontaneous period end? An inner horizon forms. Real black holes, most real black holes have inner horizons. Meaning, okay, so there's the outer horizon. Inside the black hole, there's another sphere. And charged black holes have inner horizons, and rotating black holes also have inner horizons. And since we think most black holes probably rotate, most black holes have inner horizons. Now I'm gonna explain what the inner horizon is, and well, okay, there was one more thing I want to say before I go do that. In the spontaneous period, we have, here's the band that we saw. There are no, this is an average over all the 6 spontaneous observations that we had. There are no extra bands. Here, this is a theoretical prediction which shows these extra bands. We don't have those. The extra bands are due to dispersion. They're due to the fact that in our Bose-Einstein condensate, waves, very short wavelengths can travel faster than the speed of sound. It's as if in light, in the case of a real black hole, that would be as if very short wavelengths could travel faster than the speed of light. And that causes these extra fringes. We don't see them. And I think that's because our horizon is just not steep enough, sharp enough in order to create these very short wavelengths. Okay, back to where we were. Inner horizon, what is that? Here is the potential that the effective potential that our Bose-Einstein condensate sees, not effective potential, the actual potential that we applied, the applied potential that our condensate sees. The condensate sits in this minimum, and then we said we moved the sharp edge this way to the left, and the atoms flow over the edge. But you see they go back uphill. After they go over the edge and reach supersonic speeds, the atoms then go uphill. And that means they slow down again. And when they slow down below the speed of sound, it's no longer like a black hole there. That's the inner horizon. Let's see if we, so for example, here's the density. Here's what I showed you so far. Here's the part, the subsonic part, and here's where the atoms are flowing fast. But they go uphill, and eventually they stop and form this blob over here on the right. It's as if, and so you're no longer in the region of fast flow. It's as if you fell into a black hole, then you go through the inner horizon, and you're no longer in the black hole. You no longer have the strong gravity of a black hole. It's like you're outside, you're no longer feeling the strange physics of a black hole inside. You can't ever get home because you can't get back out through the black hole, but at least you can live comfortably, I guess, in there. So, okay, so what does that do? That ends up creating, I know I don't have very much more time, so I'll try to say it fast. What's going to happen, okay, I'll just explain without going through the details too much. Here's the inner horizon, let's say. This picture was from the spontaneous period. There is no inner horizon. But we imagine that it's at a later time where there's an inner horizon here. The inner horizon can emit waves. There's an instability. Okay, I'll tell a little bit about it. Here's the dispersion relation. This is outside the black hole. You see how it curves up. That's the superluminal part. That's the part where the speed of sound is higher than the speed of sound. It's like the waves can go very fast. We Doppler shift it inside. So now that it goes negative because we said that the particles are going the wrong way. So now it's like the speed of sound is negative, but the dispersion relation curves up again. This is frequency as a function of k. Anyway, there's this 0 point. That's an instability. There's a certain wavelength which has zero energy. Due to the supersonic flow, there's a certain wavelength which you can produce for free, which has no energy, has zero frequency, zero energy. That's the instability. So the inner horizon emits these waves for free that don't cost any energy. The waves go upstream, they go upstream against going the wrong way in the black hole and hit the horizon and stimulate more Hawking radiation. Could this happen in a real black hole? It would require that there be waves that can go out of the black hole, that at very short wavelengths, like shorter than the Planck scale, there might be some waves which can travel faster than the speed of light and come out of the black hole. Start at the middle of the black hole and start at the inner horizon and come out. If there is such a thing, no one knows if there is. There are discussions about it. Then maybe it could happen in a real black hole. But but we see this, that at later times, here's this spontaneous, at later times, the band becomes very, very strong. You could see it much more clearly, this diagonal band of Hawking radiation. That's because of the inner horizon has been created, and it's sending waves which come out and stimulate more Hawking radiation. At late times, it starts to become like a sinusoidal pattern. It's because the frequency is becoming very well defined because the inner horizon only sends one frequency of wave to cause the stimulation. It only stimulates one frequency. It doesn't stimulate the entire Hawking spectrum. So you can see what happens here. After the inner horizon forms, the quantity of Hawking radiation goes way up, the green circles, much more now than the prediction for spontaneous Hawking radiation of the blue circles. Also, the width of the spectrum gets very, very narrow. The red pluses come down because it's becoming monochromatic, because the stimulation is only at one frequency. So it's becoming very much monochromatic. And this is not black hole lasing. If anybody's heard of black hole lasing, it's similar to this, what I just explained, but not exactly. And so in conclusion, the spontaneous Hawking radiation is seen to be stationary and thermal at the correct temperature. We make 6 independent measurements of the spontaneous Hawking radiation, and this confirms Hawking's calculation. We also see stimulated Hawking radiation and of a different type than black hole lasing. Now, what have we learned about real gravity? My motivation for studying analog gravity is to learn something about real gravity. Well, first of all, we learned that Hawking's calculation is confirmed quantitatively. That means we've created a system in which Hawking's calculation applies to our system, and we confirm quantitatively that his calculation is correct. And this includes the thermality, the temperature, the spontaneous emission, and the stationarity. Now, the fact that the Hawking radiation is stationary verifies the correspondence with black body radiation, that a black body should radiate, that a black hole should radiate like a black body. The thermality is the basis of the information paradox. So meaning the fact that Hawking radiation is thermal means that it doesn't contain any information, so one wonders where the information went. And we don't have any information paradox in our sonic black hole, but we should solve the paradox for a real black hole. The temperature that we see links Hawking radiation with black hole entropy, meaning remember that Bekenstein found the same temperature as Hawking. We confirm that temperature on the Hawking radiation side. We also see that the correlations are of the predicted magnitude with no reduction due to the underlying quantum structure. Meaning we have something like quantum gravity in our sonic black hole. Since our sonic black hole is made of point-like particles, that's like quantum gravity. The prediction of Hawking radiation, we treat the Bose-Einstein condensate like some smooth macroscopic wave function with perturbations on it. But in reality, it's made of point-like atoms. And that's the quantum gravity for us. That's the analog of quantum gravity. But the Hawking radiation still works. We still see the correlations at the strength that we would expect, meaning the quantum gravity doesn't break our correlation. So it means we have no firewall in our sonic black hole. There are predictions that in a real black hole there might be a firewall which breaks the correlation. So we don't have anything like that. So that's it. Thank you.
Thanks a lot, Jeff, for this presentation. We have time for some questions also at home. Yes, Vincenzo.
Thank you very much, Jeff. It is very, very interesting. It is wonderful to understand something more about this kind of experiment. Can you say something more, because it was not completely clear to me, about what it is kind of experiment is the analog of the oscillation of the vacuum that is typical in black hole and that they create, in a sense, Hawking radiation. And what is the analog of this kind of phenomenon that is typical of black hole in the case of Bose-Einstein condensate?
Okay, like this. The oscillation of the vacuum. What do you mean by oscillation of the vacuum?
Yes, in my understanding, that is superficial of what is Hawking radiation. Hawking radiation is a phenomenon strictly connected to the fact that Hawking make a calculation of quantum field theory effect on a curved space-time. And the point is that in a sort of very, very simplistic presentation of this kind of calculation, one can say that if you have a typical quantum field theory phenomenon that is creation of a couple of particles and antiparticles, that this kind of, if this kind of phenomenon is on the horizon, this is one of the terms clearly of the calculation, but the most important one. And this great, okay.
You mean the fluctuations of the vacuum?
Yes.
Okay. Yes. Sorry. Yes. I understand now. Yeah, it's okay. It's okay. I thought it sounded more exciting, but anyway. So so these pairs are one way to think of Hawking radiation. Pairs are created. One of the particles manages to cross the horizon, say, into the black hole, and there it can exist. Like the picture is all around us, pairs are created, a positive and a negative energy. They can only exist for a very short period of time before it truly becomes a true negative energy particle, which is possible. Anyway, if this negative energy particle goes into the black hole, there it can really exist as a particle, and then these two particles can just become free, and one comes out to us. So, can one picture the same thing? Yeah, one can picture this, the Hawking radiation in the sonic black hole in the same way. We also have this the same calculation involving the spontaneous vacuum. There's the vacuum term, the vacuum production of particles with no incoming particles. We have the outcoming particles. So if you want to think of it that way, you can. We have the negative energy particles inside the black hole, and they can't exist outside the black hole, the negative frequency ones that we talked about due to the Doppler shift. So we also have negative frequency particles. So you can use the same picture, same idea for ours. Yeah, and that's very important to have the Hawking radiation in any system. You need negative energy modes. So you can have the negative energy and the positive energy making zero total energy. You're welcome.
Stephan Hartmann.
Yeah, thanks very much for explaining these amazing experiments.
You're welcome.
That's really good.
Thanks.
I have a question about what we can learn about black holes. And
Okay.
I mean, there are all these analogies between the systems, and you worked out much more in the last couple of years. But you said Hawking's theory is confirmed, or Hawking's calculation is confirmed, but the materials are totally different. A black hole is a different physical system than a Bose-Einstein condensate. So I want to ask you about your view about how this works. How can I confirm? I mean, the phenomenon type seems to be the same, but the physical realization is different, yeah? And so how does the confirmation work? Philosophers are concerned about this, and we have debates about this. And I'm tending more and more in the skeptical camp here. So I wanted to ask you to explain a bit more how it works. Actually.
Okay, well, what I meant, I wrote very specifically, Hawking's calculation is confirmed. I didn't say Hawking, a real black hole will definitely radiate Hawking radiation. That's not on this, it's written here. I say his calculation is confirmed. We've created a situation where his, what Hawking has assumed in his calculation is met by our system. And so his calculation should apply to our system, and it indeed does. He didn't forget some factor of 2 somewhere or something. We prove no. Quantitatively, his calculation was correct. So that's what we confirmed. His calculation is a semi-classical calculation. He has, as you say, he has some background and some fluctuations, classical background and some fluctuations on top, and our system has all of that stuff. So I hope, and I'll be very happy, very interesting to hear all the philosophical discussions later about this.
Okay, 2 brief questions. Marco Sanchioni.
Thanks. Just a curiosity. So about the thermality of the spectrum, because, lately people have tried to show that you can, in some sense, have a unitary and firewall-less evolution of the black hole. And basically, they try to say that Hawking calculation was correct, but incomplete, since you can add like non-perturbative effects. And this would show that the entropy of the Hawking radiation is not growing all the time, but at some point start to slow down at the pace-time, this so-called pace-time. And so Hawking radiation should not be thermal, but at some point should have correlation between the Hawking quanta. This is like in the model in which black hole evaporation is unitary and firewall-less. So I was curious to say, and I mean, these correlations, they should be beyond some complex boundary in which an asymptotic observer cannot detect them. So in some sense, from the empirical point of view, the unitary and non-unitary evaporation should be, there should be an underdetermination between the 2 computations, the Hawking one and the one with the non-perturbative.
They should be on a boundary? You said,
yeah.
What boundary? Boundary?
No, I mean, asymptotic observer collecting Hawking radiation cannot see really this correlation between but I was just curious if you see some deviation from thermality in your experiments.
Okay, first of all, no, we don't see it, but there are some people who would like to include the effect of the analog of quantum gravity to do beyond semi-classical calculation, and then they could tell us how big, if there should be a deviation from thermality, and how big it should be. Our system is very much in the limit of semi-classical limit. It's very big. You could say our black hole, it's like a big black hole, meaning, remember I showed you this picture, you can sort of see it here. I don't know if you could remember what this slide looks like. There's the long, thin thing. The width of this long, thin black hole, analog black hole, is fat. It's fat, meaning it's many atoms wide, you can say. And that means that the quantum effects should be very small. In the beyond semi-classical, the quantum gravity effects should be very small. So it's like a big diameter black hole. So if we can do an experiment with very much fewer atoms, which will have a big problem of signal to noise if to do such a thing. But if we could do that, then we could maybe see beyond non-thermal effects. Or someone would also make a prediction. It's very hard to do these calculations, even like quantum gravity calculations, even though the theory is known in the Bose-Einstein condensate, it's still very difficult to make the prediction. So I hope that answers your question.
Okay, last question by Karen Crowther.
Yeah, thanks.
You're welcome.
I'm just curious how your results compare with the other groups using the different setups and the different mediums, and kind of how you view your results in comparison with them. Like, what's special about your particular setup? As I understand, it's to do with the particular way you're using the quantum aspects, right? The quantum optics. And yeah, maybe this ties in as well. What role is the quantum playing there?
Okay.
Yeah.
Our system is different from the other experiments because it's very cold. And that means we can see the spontaneous effect of quantum production of the Hawking radiation. However, Hawking radiation has a quantum aspect and a classical aspect. That's why it's called semi-classical. The classical aspect is like the black hole is classical, like a real black hole is classical as described by general relativity, and then you have the quantum on top of that. We see that quantum on top of that, and the other groups aren't cold enough to see that. What he was asking about, I think, was quantum gravity. That means even the black hole is quantum. It's not classical and quantum, it's quantum and quantum. That we can't see. Our black hole is too big to see that. So I hope that answered your question.
Thanks.
Okay, you're welcome.
So again, on this issue of, okay, so what's special about the experiment? Okay, so it seems like Andrew has this theorem that says that after all, quantum noise is classical noise. And so that maybe, we didn't need to look for the quantum effect, really. We could also be satisfied with the classical one. Do you have any views on this? Am I misreading the theorem, or do you have any thoughts on?
I'm not so familiar with what you said, but what Unru's theory, I think that, yeah, I think I heard Unru explaining how we can get the information from just the class, from scattering. It's true, if you scatter away from the horizon and create pairs,
Right.
or if you have the vacuum fluctuations creating the pairs, it's a similar process, and you can learn about this pair production from either experiment. But I guess it's nice to see the spontaneous quantum effect, that the quantum field theory also works in this system. So it's nice to, I think, to also see the quantum aspect.
Okay, yeah, thank you.
You're welcome.
Okay, thanks again, Jeff.
You're welcome.
Next speakers are online. Are Lina Jansson and Silke Weinfurtner from the University of Nottingham, and they will speak about analog simulators.
Video. There we go. Thank you. So first, let me just say thank you very much for inviting us, and apologies for not being able to be there in person. I would have loved to be able to deliver this talk in person myself. Unfortunately, I'm still a little bit under the weather, so I'm joining you online and keeping my germs to myself. So I'll jump straight into the talk. Now, this is a talk in two parts. Now, I'm starting, and I am going to argue that a particular take on Lipton's challenge, or why we should live in the loveliest of all possible worlds, or why explanation should play any role in confirmation, also allows us to say something new, and we can see how interesting you think it is, about how we can turn greater explanatory access from analog simulators into greater empirical evidential access for the behavior of the less accessible system that we're interested in. Now, after my part of the presentation, I'm going to hand over to Silke, who will discuss one particular such simulator, a cosmology simulator, and talk about some of the extensions of one of the upshots of my presentation, which is to argue for the importance of experiential understanding in interacting with the simulators in an art collaboration that we've both been part of. So let me get going. Now, I don't think that I need to say too much about this slide for this kind of audience, but it's helpful to acknowledge sort of up front that there are a range of interests that we might have in mind when we think about why we are interested in analog simulators altogether. Now, often it is because direct experimentation is either very difficult, if not outright impossible with our current state of knowledge. It sometimes has very interesting applications for building understanding about theoretical models, where those models might be the models that apply to the simulators themselves, not necessarily the less accessible target system. And there's also been arguments already in the literature about the value for various heuristical reasons for theory building and so on. So I want to acknowledge early on that in this talk, I'm limiting myself to quite a narrow problem, and it's one that philosophers have been particularly interested in, which is whether or not we can use analog simulators to gain empirical evidence for the behavior of relatively inaccessible systems. While giving a heads up that I know that this is not everything you might want to do with these kinds of systems. And what I'm going to try to convince you of is that the explanatory gain that we can get, and I'll try to show you why I think we can, the explanatory gain that we can get from analog simulators can enable indirect evidence for their reliability as guides to the behavior of the relatively inaccessible systems that we're interested in. And that in doing so, we have a kind of answer to Lipton's challenge. So while it's not going to be the case that explanatory loveliness can be a guide to likeliness, I think that explanatory loveliness can turn out to enable it. It can turn out to make available certain types of empirical evidence that we couldn't have without considering directly explanatory hypotheses. So let me say a little bit about the kinds of reasonings that I have in mind and what I mean when I say that explanatory considerations can enable confirmation. So I first need to say a tiny bit about what notion of explanation I have in mind. And as many of you in the room already know, this is a huge topic in its own, on its own, and we could have a talk only on this. So luckily for the purposes of this talk, I need to make use of something that is not incredibly strong and at least relatively uncontroversial, namely that I take explanation to have a hallmark of being closely tied, closely linked to being able to answer questions about what would have happened if things had been different, or more generally, explanation is closely tied to subjunctive reasoning. Now, there's various ways in which we might spell this out in more detail, and we might tie it as being constitutive of explanation or not. And I have my own view about what the preferred way of doing that is, but here I just need this more broader connection. So taking that on board and accepting that explanation is tied to subjunctive reasoning, we already have wonderful examples from the history of science of the importance of considering explanatory reasoning or subjunctive reasoning in order to enable us to generate evidential reasoning from our empirical access to a system. So in particular, Bill Harper and George Smith have undertaken sort of extensive studies on Newton's methodology in the Principia and shown how at various junctures Newton looks like he's relying crucially on subjunctive reasoning. Now, this reasoning is really crucial because what it allows Newton to do is to start from a very idealized system, such as, for example, assume it's a two-body system, but then also taking the theoretical framework he's built to be responsible for accounting for deviations from that idealized structure, so that he accounts for the fact that there is precession of the moon in terms of the disturbing influence of the sun. And for this kind of reasoning to work, it just isn't possible to apply something that involves merely a straightforward entailment from the laws. We really need this kind of subjunctive reasoning and going through the steps of idealization. And in this sense, the explanatory hypotheses that Newton is working with allows for evidential reasoning that the mere predictive equivalent of those hypotheses doesn't. And nor is the kind of success of this reasoning somehow trivial or guaranteed. So we have a reasonable case for saying that when this kind of reasoning succeeds, it gives us some indirect evidence that the explanatory model that, or the explanatory hypotheses that we used, have gained some evidence. They really are reliable ways of reasoning subjunctively. So famously, one of the shining successes of this reasoning is accounting for the leads to the prediction of Neptune, and we also have the self-correcting nature of this kind of reasoning in the eventual failure to observe Vulcan. So far, what I've tried to very quickly convince you is that hypotheses about explanatory structure are sometimes incredibly useful, even if we don't think that they directly sort of give a theory a confirmational boost. They can enable confirmation by unlocking reasoning predicated on the assumption of the hypothesized explanatory structure that isn't readily available without those hypotheses. And in common with Lang, nothing that I've said so far is sort of in tension or incompatible with a Bayesian account of confirmation. So while it's true that Bayesian accounts often don't directly consider degrees of beliefs in hypotheses directly about explanatory structure, taking that to be this kind of subjunctive structure, there's nothing that prevents a Bayesian from doing so. It's kind of open to have hypotheses about explanatory structure, just like many other things we might be interested in. So with that on the table, I can say a little bit about why I think this is relevant to the debate about analog simulation and whether results from analog simulators can give confirmation of our theoretical models of relatively inaccessible targets, such as astrophysical systems or theories about the early universe. So I know that there's lots to say about this debate, and it's independently very interesting, but because I'm going to end up trying to suggest an alternative way of thinking about things, I want to highlight just a few things about this much larger philosophical debate that has already, that has taken place and that is still ongoing. So the thing I want to highlight is that in the predominant way in the current philosophical literature of thinking about this problem, what's really interesting about analog simulators for confirmational purposes is partly just that they instantiate some relevant mathematical structure. And that we have the model of the simulator system and the model of our target system linked by some universality argument or potentially conclusion of some universality argument that allows an increased confidence to flow from an increased confidence in the empirical adequacy of the simulator model to an increased degree of confidence in the empirical adequacy of the model of the target system, if this way of modeling is legitimate. So to make this just a tiny bit more intuitive, we could apply these to several cases, but the philosophical literature has largely focused on Hawking radiation. So putting some specific examples in there, we could imagine that we have in our simulator some specific data at the kind of bottom of this arrow here, closest to the articles. And that data might end up offering some confirmation for a specific model of our simulator system. And insofar as we increase our confidence that this model is really empirically adequate, we might also have some reason to become more confident either in the, so it was interesting to hear this earlier, either in the argument itself, the calculation of the universality argument, or potentially just in the conclusion of it, which might then make us more confident in our model of the less accessible target system. Now, I think that debate is fascinating as far as it goes, but I do think it raises a few puzzles. And what I'd like to do here is to focus on the last of these puzzles that I've listed, and show why I think that there is value to be had in considering an alternative way of conceptualizing the conformational structure between the analog simulator and the target system that we're interested in, such as the behavior around astrophysical holes or the early universe. So I'll start with the last of these examples. So as the people involved in this debate are very clear about, a consequence of thinking about the structure in the way that I had on the previous slide is that if we become completely confident in some universality argument or in some conclusion of a universality argument, that blocks any further role for analog simulators. There's no longer any more confirmation to be gained from analog simulation or experimentation. While I think that's completely correct as far as the Bayesian analysis goes, before we encounter a Bayesian analysis, there's something about that is a little bit surprising. So setting aside for the moment the Bayesian analysis, we might have thought that if I become completely confident that there is a relevant link between my simulator and my target system, such as my astrophysical or cosmological system, such that I can transfer conclusions from the simulator to the target system, then that would be the best possible scenario for me to be in. That would be when I would have a kind of perfect simulator. And you might think that, well, the closer I get to that, shouldn't that improve my ability to draw conclusions about the simulator? About the target system from my simulator. And there is a way in which I think that we could do something to reconceptualize the scenario to preserve that kind of idea, rather than thinking that we have to have one structure where we go via the universality arguments. And if we become completely confident in those, then we then have to move to a completely different structure for capturing this new type of reasoning. In particular, the suggestion I want to make is that we could think of our reasoning as being mediated via a hypothesis about the simulator system and the relatively inaccessible target system having shared explanatory structure. Now, the benefit of this is that there is now logical space for becoming completely confident in there being shared explanatory structure, while still remaining unsure or completely ignorant about what the actual explanatory structure is. Now, this means that even in the face of complete confidence in shared explanatory structure, there's still a role for analog simulation to play. That would then be telling us about what the actual explanatory structure is for both cases. Now, at this point, I'm imagining that a few of you have the objection. We're going to say, well, that's perhaps in some sense logically possible, but a scenario like that could never happen, because to become confident about there being shared explanatory structure between the two cases, I would need to see what the explanatory structure is in the two cases and then compare them. And of course, once I have the explanatory structure in place of the two cases, then that would again block the transfer of confirmation from the analog simulator to the target system. So what I want to do in the next few slides is to address that, and in doing so, I will turn out to address also my kind of second puzzle for the Bayesian debate, namely the idea that the idealizing assumptions beyond those that are explicit in the universality arguments seem to carry physical information that seems to be lost. So let me say something about where this thought comes from, that I could only really seemingly become confident in there being shared explanatory structure if I know what the explanatory structure is in the two cases and I compare them. Now, one reason why I think that this seems to be the case is that we often operate of an idea of explanatory structure that takes explanations to be a largely abstract, mathematized phenomena. And analog simulators don't look like they are mathematical models. They look much closely related to concrete models. They look much more like models such as the model of the San Francisco Bay Area that's constructed to try to evaluate the plan to build dams in the San Francisco area, where both the model and the target are concrete systems. And our notion of explanation often looks much closer to mathematical models, where what we are dealing with is an abstract entity, such as a mathematical model, here a simple pendulum model, that has a concrete target. And I think that there are good reasons to try to resist this way of thinking. So from the literature on explanation, even when it focuses, as I have also done many times, largely on these kinds of mathematical models, it's generally acknowledged that merely having a mathematical model is not enough to actually have an explanation. We typically need something else, such as, for example, understanding of what happens under interventions, or if you're me, understanding of what happens when the conditions of application of the model are violated, when they start to fail, when we kind of push the model to its breaking point. And analog simulators are particularly well suited to offer exactly that kind of knowledge. So analog simulators, even though I've said that they are largely concrete models, and here this is a picture from the Gravity Lab at Nottingham, they still, of course, come with lots of mathematical models associated with them. But those mathematical models themselves typically also, well, yeah, they do, come with their own assumptions that we need. So we typically have to make quite strong assumptions to get the mathematical analogy off the ground, and we can ask lots of questions about what starts to happen when those assumptions start to break down. And answering those kinds of what if things had been different questions is closely tied to getting the very conditions in place that allow us to take the mathematical models to be explanatory in the first place. So in the last few minutes, let me say how we can exploit this kind of gain in explanatory knowledge to leverage it towards increased evidential empirical access. Now, the first thing, of course, that it does, which I think is highly non-trivial, is you start to have an ability to really understand what the explanatory structure of your mathematical models actually are. And here's the kind of main point that I made earlier, which can be summarized as, it's not all in the mathematics. Of course, it's not to say it can never be in the mathematics. If you could embed your theory in an already well-confirmed, deeper and broader mathematical structure, you might be able to evaluate these what if things had been different questions in a purely mathematical way, but very often we can't. And direct experimentation and empirical access is a great way of doing it for many cases. Now, the second step which we could take once we have that is that it can allow us to enable measurement-mediate calculations or conclusions that we simply cannot easily do analytically. So one of the really interesting things about looking at this is once we have a physical system, we can allow ourselves to reason about what happens when we start to violate some of the idealizing assumptions that go into deriving the mathematical analogy. And it's often sometimes possibly outright impossible, often at least very, very non-trivial to figure out what that would be. Now, the final step we could take is we could simply hypothesize that the target and the simulator have a shared explanatory structure. And similar to Newton's case, we could then try to reason based on that hypothesis. And the empirical success or failure of the reasoning predicated on the assumption of shared explanatory structure can provide us some indirect evidence for whether or not the analog and the target system actually share the relevant explanatory structure without being able to directly have spelled out what that explanatory structure is and comparing it in a mathematized way. Now, this doesn't work without some empirical access to the astrophysical or cosmological target, but it enables greater evidential empirical access than we could have without the simulators. And just like standard Bayesian accounts, because we haven't violated anything of the standard Bayesian frameworks, unsurprising success matters less. So in particular, this means that reasoning that explores beyond the confines of the mathematically established analogy matter more, because they're more surprising that they would continue to hold. And explanatory reasoning here, so philosophically, one of the really fascinating upshots is that explanatory reasoning here is unlocked not by a new, deeper theoretical framework, as it was in Newton's case, but by greater empirical access enabled by the simulators. We're sort of reasoning directly through the simulations to what we would think the explanatory structure is. So at this point, I just want to say thank you to lots of people, particularly the Gravity Lab and the Art Lab and Marco, who have spent time talking to me about this. And I'm going to hand over to Silke.
Yeah, so I'd like to talk about one specific experiment, which is a bit different from black holes. It focuses on cosmology. And it also is a way to address the question, what can we really learn from these simulators? And so starting with the title, so from one to few to many, that's kind of describing the physics that happens in the system. The system is being a two-fluid interface system, and we're looking at the interface waves that form in the system. And what we do, we study the wave dynamics, and then I will point out how this wave dynamics can be mapped to the dynamics in the early universe, and in particular mapped to cosmological preheating. So the system is a fairly simple system. What we have here, if you look to the right, you see that is a sketch of the experimental system. It's at the moment, this is a classical system. We're currently transitioning to superfluid helium, but this is the experiment I'm going to talk about. And in particular, what it is, you see here one, that is what we call a bespoke acceleration platform. That's something we built, and all that thing can do is it can shake up and down without any harmonical distortion, or with reduced harmonic distortions. So it's a very steady system that goes on pneumatic bearings up and down. It is built to host a fluid cell. Fluid cell is about 10 centimeters, with around 10 centimeters in scale. It hosts a two-fluid system, an immiscible two-fluid system. You should think about the same as oil and water. And the way we do it, we fully enclose it. There is no air in there. It's just these two fluids that don't mix, and they form an interface. And it's that interface that we are interested in. And what we do in order to study this wave dynamics in great detail, we have a camera that monitors this interface wave. And over the last 8 years, we developed very accurate detection methods. So the fluid is enclosed. It can't evaporate. Hence, it allows us to have a sample cell that can live for many, many days. So we can have thousands of repetitions of the same experiment. Okay. Right. And so what we want to unravel is, if you take that two-fluid system and you start shaking it, we want to follow the wave dynamics in the system. Okay. So this here is on the left. What you see is actually taken from experimental data, where we extracted that fluid interface over time. Okay. And so the time scale is not accurate. I think it's a bit faster here in the video as it is in real time. And what you see, we start shaking it and we start to see that we form some interface waves. So this is really extracted from experimental data. And as you see, as the times progress, you start to see very clear pattern, very clear eigenmodes in the system being excited. Okay. And as you continue, these modes are getting larger and larger and larger. And eventually this pattern becomes a bit more interesting, a bit more involved over time. And we want to study this behavior as the system keeps on being driven through this shaking platform, which it's resting on. And we want to understand the whole nonlinear wave dynamics. We want to unravel it through careful data analysis. So what you see here on the right, that is something that will come through. We'll come back to it at the end, towards the end of my presentation, and Lina already mentioned that. This is actually a print of one of these interfaces, and that has been 3D printed by the artist Alistair McLeod, and highly polished 3D printing, but this is an actual sort of a wave dynamics frozen in time. Now, what I want to say about this is you have a shaking platform, right? And what you are, the drive is at omega d, and the wave that you're exciting is at half of the driving frequency. So you're exciting these eigenmodes in the systems, and this we try to understand a bit further. I want to say that when you look at this interface, and you can assign this a function psi that changes over time, and it depends on the radial component r and on theta, which is the angular component. And you can split this in a time-dependent part and in a spatial eigenfunctions, which are, because of the shape of our fluid cells, these are simply the Bessel functions. So these are the eigenmodes of the system. Okay. Now, if you look at the mathematics of this wave, so if you say, okay, I'm starting with a complicated Navier-Stokes system. In principle, there are these two fluids that don't mix, but they share this interface. Now, what you can do is you can derive an effective field theory. Okay, and when I say you can derive, there are many different approaches as how to do it. It's not like a unique consensus of how to do this best. But we are following prescription introduced by Miles, and what I'm writing down here is perhaps a bit more complicated, but it's easy to understand. So we have a perturbative ansatz. We are writing down the Lagrangian for the system, and what is important is the way we ordered this. So L2, L3, and L4 means at which order in perturbation theory, okay? And again, this is easy to understand. So what we have here, we write this down in terms of this psi coordinate, right, that I introduced. So this is this time-dependent parameter in the system, how the field amplitudes are growing over time. And what we see here is that if I look at that first line here in my Lagrangian, and you look at this, we only have these psi a's in there. So these are terms for each mode. So psi a means it's a particular mode and how this mode behaves over time. And what this means is that part that we call this linear field theory. And what this means is if I have a wave, this wave can be in an ocean, for example. On the ocean can be an interface or an ocean wave, and it travels along without being bothered by the other waves in the system. And we talk about this a free wave. It doesn't interact with the other waves. So this is the linear part of your Lagrangian. But as you go on to higher orders in perturbation theory, the terms are changing, and they're changing because here now we don't only have the single wave of Xi A, we have Xi A, Xi B, and Xi C. And these are all different modes, different waves in your system. And what that means is now I cannot think about this wave just going through, you know, traveling on this interface without seeing the other waves. It starts interacting. And when things interact, interesting physics can happen. You know, two waves can come together and scatter into another one. So you have nonlinear field theory, or you have particle scattering processes. And this is what we are particularly interested. And now as you go on, this is very complicated. These parameters needs to be calculated. This is not any free terms simply postulated. This is really derived. And then you have analytic expression for the coefficients in there in terms of the fluid parameters and so forth. So the densities, the heights of the two fluids and so forth. Okay. Now again, we have these coefficients here, right? These coefficients can be split. So this is my interface that changes over time, depends on the radius and depends on theta. And you can factorize that into a time-dependent part, which is sort of the time-dependent amplitude of the waves as you progress in time, how the waves can grow. And then here, this FMK is simply what we call this a spatial mode function. Is the part that I can split off that doesn't change over time. Okay. And I will come back to this part, but first we need to just understand when you have a system like that and you start with very small amplitude. So we start with just this fluid, this interface at rest. Now, so there are some small variations in the system, but by all means, what you should think about is these are very tiny wave amplitudes. Some vibrational noise will always excite some of the waves in the system, but they're really, really small. And when they're really, really small, we're in this regime where the waves can coexist in this basin without scattering or interacting with each other. So this is our linear field theory. Here, of course, we have damping in the system, right? It's not an ideal fluid. It's not like Jeff's system where you have this beautiful super fluid. This is a normal fluid and you have damping. And whenever you have damping, you need also a sourcing term. This is the fluctuation dissipation theorem. And that needs to be, of course, taken into account in the linear theory. Okay, so this is my sort of linear wave equation that I can derive from the first term in my Lagrangian. Okay, and the rest are just these parameters which are given through my fluids, the densities, the surface tension. All of these things, of course, have to enter in this equation because they determine the wave's dynamics. And what we also have here, which is interesting, because I rested that basin on a shaker platform, what you have is now you have this capital omega of t, and that contains this capital F of t, and this F of t is simply the driving force, which is provided because it's resting on a shaker. Okay, so it's all very simple physics in a way, no, that we're all familiar with. It's also referred as the Faraday instability. And we all have perhaps seen sort of on videos or in demonstrations, this sort of funny pattern forming if you take a fluid system and shake it parametrically. And what's happening is simply a material equation and you get a Fourier instabilities. That's what it is. And what it means, there are some very well-defined frequency in the system that are unstable. And these things will form not because the waves interact with each other, but an individual mode in this system becomes unstable and gets parametrically amplified, and it grows exponentially in time. Okay, and now let's look at the long-term dynamics, which is what we're really interested in. Sorry, I just made a mess on my desk. Just a second. Okay, good. Right, so let's look at first to understand this physics a bit better. So we have this basin, this two-fluid cell, and we're interested in this interface, and we want to see how the waves form over time. And the first thing one has to understand is just like the eigenmodes of a drum. When you hit a drum, you can excite eigenmodes in the system. And any excitation that you have in the system will always be, at linear level at least, a superposition of these eigenmodes, different eigenmodes of your drum, different eigenmodes of interface waves in this system. And we can characterize them with two parameters. And these are here these two numbers, and the first is called the azimuthal number. So if you go around, you take a fixed radius and you go around on the angle, go once around, how many wavefronts do you count? And so that gives you the azimuthal number. And then the radial number is also if you go from the center on a fixed angle out radially, how many wavefronts, how many nodes are you counting again? And this is your radial wave number. So you have your azimuthal and a radial wave number. And these determine which eigenmodes these are. And the higher the numbers get, the more of these little blobs you're getting, because the higher are these Bessel functions. So, and any excitation in your system, because it is a finite size system, has to have, can be decomposed onto this eigenmode basis. Okay? And this is what I refer to as the spatial profiles before. And now what you can take in, if you have this parametric resonance, you can take one of these nicely defined waves and you can raise their amplitudes. And this is precisely what's happening in this system. Because it is exposed to parametric resonance, what you do, you take one mode in your system and you make it very large. Okay? So this is some very intuitive physics. It's not difficult, and it's really interesting because that's precisely what's happened in the early universe when we talk about the mapping. So the system mode that is predicted to be unstable is the mode that we label as 4,1. So it's this first mode here. And what we are looking here on this panel here is on the y-axis, there is the amplitude of these eigenmodes. And we have different lines. We're looking at different eigenmodes in the system. And now we see how over time their amplitude is growing. How big this particular, blocks or units of waves, how they grow over time. Now notice that our signal here starts below 1 micrometer. So this is when I was referring to this high control and developing these detection methods, is to allow us to see these waves when they're really, really tiny. And as time progresses, these waves start growing. And what you see that this first mode that we call the dominant mode is the first one that starts to trigger off, gets larger and larger, and at some point it gets arrested. It cannot increase its amplitude further. And this allows us to define 3 distinct regions in this wave dynamics. So the first one is, and I have to say that initially they all seem very flat. And the reason for this is because our detection method is capped below 1 micrometer. Okay? And so it means initially it's just noise in the detection method. But after some while, this wave that we excited, this m equal 4 and n equal 1 mode, this very red line, starts to grow exponentially, is a log plot. And so then what's happening after a while, more waves are forming. More of these eigenmodes seem to pop up and getting populated. And then eventually all of the modes are arrested, even though you keep on driving the system parametrically, you're not exciting more. And you reach a far from equilibrium steady state. And this is the hallmark of a spectral cascade, where you go from one to few to many, and also in some cases, you can develop full-blown turbulence. So this is the wave dynamics in the system. So we have one mode is excited. Here we plot now the signal over k, over the wave number. We see we start here exciting one mode. If you go on, more and more modes are excited, and eventually we form a spectral cascade, where it means that you find a simple law, a power law, as how to describe the amplitudes of these waves relative to their wave number. So you find a new order. And what's interesting is that the early universe undergoes the similar or the same stages in its dynamical evolution. And I will make this mapping, but this is simple physics that we've all seen or perhaps looked at, is something actually complicated to understand when it comes to early universe cosmology. Okay, so we understand what happens to one mode, we know how it gets excited, and we know the late stage is what we call this spectral cascade, or this far from equilibrium steady state. And now we need to look in this region in between, and this is precisely what we wanted to understand in more detail. And the way this works is now, in order to understand this few mode regime, we now need to look at our Lagrangian not in the part where one mode can be described entirely by itself. One mode now interacts or gets bothered with the other modes in the system. And we know how to do this because we know this from particle theory. So what we're looking at is scattering processes, okay? And so what I can say, well, if I have modes in my system, like I have this 4-1, this dominant mode, then I can look at selection rules as a first instance and say, well, how can this, if I have one mode that's really large, how can this actually create another mode? How can it create one with m equal 8 and n equal 2? So how can it create another eigenmode in the system? And there are these selection rules that we know how to do this in particle physics, and the same applies to our shaker system. And then you can write down all the possible scattering processes that are, within, that don't violate a certain conservation in the system, such as, for example, the azimuthal mode number has to be consistent. So 2 modes with m equal 4 have to scatter in a mode with m equal 8, and so forth. And then you can write down always more and more and more complicated scattering processes. And what we can do in these experiments, we can actually, at some point, at the early points, we can catch if actually these modes are indeed excited, if they follow the scattering processes, just as we know it would do in quantum field theory or in particle physics, that it has this really clear track that you have. And indeed, when you do this, you can extract this information and show that every mode that forms is within that rule book or set of rules that we have. But we can do much more. We can use the toolbox of statistics to then say, well, at the later regime, or if I look at 2 modes, I can say, which one of my processes that I wrote down here is actually responsible that this mode formed? So how did I get to the 8.2 mode? And we can actually do this by asking specifically, going through our data, which one of the scattering processes occurred by looking at correlation measures. Okay, so we can do 2 things. We can first follow individual modes. And then what we can do, see which scattering process caused this mode to be created. And then as things going on, of course, you can ask something else. You can say, well, once I have so many modes in my system, then surely I cannot follow each mode because there are too many interacting and there might be one scattering process causing this, one mode to appear, but it can also be sourced by something else. And what you can do at the late stage, when you're in this many regime, in the spectral cascade, for example, what you can do is you can ask which hierarchy of scattering processes occur. And I can look at if this is 3-mode scattering, as for example here in this corner, or 4-mode, or 5-mode, or 6-mode. So you can extract all orders of correlation functions, and you need to look for cumulants or connected parts, which is a technical detail which we explain in our paper. So what you have is a really cool tool to understand the scattering, the intricacies of the scattering process in a system. But it's also a really cool tool in another way, because usually when we do this and put it on a computer, what's happening is we have these many interacting modes, right? And eventually these things are hard to simulate when you add more and more and more modes to your system. So these are generally, to calculate this kind of scattering processes with increasing complexity is hard to simulate. But in our analog system, all modes exist. They're naturally there. It's a many mode system, and when the amplitudes are getting large, they will interact. So in this sense, it's a beautiful system to study these intricate scattering processes. And now I'm sure I'm running late, and I'm coming to my 3 concluding slides. How am I doing time-wise?
A few minutes.
Perfect. So we have a system that we can monitor carefully over time, that we can first excite in a concrete way by studying parametric resonances, then study scattering processes, controlled scattering processes, and their late time behavior. Now, this particular system that we're looking at is also an open question in weak wave turbulence, where effects such as finite size effects on resonant interactions and on wave turbulence are not that well understood. And where also things like finite effects, finite size effects, boundary condition, and strong forcing, these are all effects, all sort of environments or circumstances that are within the field of weak wave turbulence, where this kind of physics usually belongs to, are not well understood. So in particular, there was an open question if you would form a spectral cascade. So from this, it closes a gap in the weak wave turbulence community when looking at the formation of spectral cascades under strongly driven significant finite size and amplitude effects. Okay, so this is just sort of why this is interesting from a fluids perspective as well. And the reason also why this is interested, this kind of physics, often in weak wave turbulence, many looking at fluid system is often the first step, but weak wave turbulence is very broadly applicable across many, many systems. And this can be mapped to different physical systems, even to economical modeling, to climate change, many different systems where this is coming in. Okay, and then what we have done here, in order to unravel really what the physics behind this, we could show that all the laws and terms from weak wave turbulence, which constrains the kind of interactions that occur in these systems, are indeed the ones you would usually consider in weak wave turbulence. We did this by taking things developed in particle physics and quantum field theory, and we simply applied that to this classical two-fluid system. And now comes perhaps a bit late, but I think that because it is such a strong analog to something that happens in the early universe, and I always feel like looking at waves on fluid interfaces, it's much more relatable. So since you understood the whole physics already, now I just need to tell you how to map this to the early universe. So when I say the early universe, it undergoes, you know, several different stages. We're really talking everything that happens in the far below the first second. After the Big Bang. So we have a inflation of rapid expansion, inflation, and at the end of inflation, what it is following this cosmic inflation, you have this inflaton field, okay, and this inflaton field carries all the energy, and this inflaton field at the end of inflation is rolling down this potential. And in this potential, there's this minimum, and this inflaton field goes up and down, okay? And what it happens is that this inflaton field gets parametrically excited. And what this inflaton field then does, it couples to the matter fields. And because of these interactions, it then parametrically excites the matter fields, and then the matter fields, what they do, they get larger and larger amplitude, they start to interact with each other, and also decay their energy by simply exciting more and more fields. And the question is, how do you thermalize through this process? What are the late stage dynamics of this complicated nonlinear field theory? Okay, so inflation ends, the energy stored is stored in the inflaton, which is a hypothetical scalar field, okay, that is conjectured that it has been responsible for cosmic inflation at the very early universe. Okay, at the end of inflation, because at the end of inflation, all the matter fields are frozen out, and we need to find a mechanism that thermalizes the field again. And it's this process that should be responsible for the thermalization of the early universe, and we need a thermal universe to start the nuclear synthesis. Okay, so super important part of physics that we really need to understand, hard to analyze. Now we're talking about quantum fields going through this. And this is what we're trying to comprehend here. So the inflaton has all the energy. It's stored in this inflaton field. This becomes an oscillating field, like a ball in a ball. Then this drives an explosive particle production via parametric resonance, okay? And then what's happening is you pump all the energy into the matter fields into a dominate mode, and then it starts this, it needs to then distribute this energy within all the other field modes in the system, okay? And this is how the universe has to heat up, or is conjectured to heat up, and it succeeds the hot Big Bang. Right. Now, this is all very good. Seems like a really good plan of how, you know, you get out of this predicament that the universe is basically frozen at the end of inflation. But the problem is that numerical simulations, they only get you that far, and after the few mode regime, they're actually breaking down. So, and even the state-of-the-art cosmological lattice simulations, they struggle with this, and this is just how it is. And why is it important? How this process works tells us exactly, you know, it's adding to the timeline of the universe. How old is our universe? And this is an important part. How long does it take the universe to thermalize? Right, and this is where we come in. Now you can make the mapping. So the shaker is our inflaton field. So we are externally exciting that field. The interface waves are my matter fields, and the wave-wave mixing is the interacting matter fields in the system. Okay, and so what we are now doing, we have identified the exact mapping or translation key between my target system, which is the early universe, single field inflation model, and our concrete or physical system, which is my shaker system. And once you have the exact mapping between them, you can then tune parametric experimental parameters to resemble, to implement a physically interesting part of the parameter space. And you can then, of course, go away from looking at single field parametric resonance seed to broadband. You can add some complication to the experiment, all of which are really hard to comprehend analytically or on a computer. Okay, and that's to end on a really high note. As I mentioned, perhaps all of you have in one way or the other seen these Faraday waves. This is a really pretty pattern. So you put a little water basin on a speaker, and then you see this beautiful pattern emerging on this interface. And then what you can do, and this is what Alistair McClement, our artist who worked with Lina and myself as well, and is by now part of also a scientific team. What he did is he set up a shaker system, and he is very crafty with creating these beautiful projections where you project this emerging wave pattern onto a screen. And what he did, he set up a particular fluid cell. He changed the frequency as you go through. So he put together an artwork. And if you are in this room, suppose you're in this room, he changes the frequency of the speaker, which means that the frequency of your shaker system is changing. And he chooses the frequency regime in two ways. He chooses the system size and the frequency in the following way, that as you ramp through this frequency, you change the eigenmodes in this basin. So you get to see a number of beautiful pictures going through in your mind. But you're in this room, and this room has a very low frequency, huge, which you don't see there, another speaker in there. The system size of the fluid cell is chosen such that the frequency that excites these pretty patterns is a frequency your body responds to. So now you are part of the experiment. So these parametric resonances create resonances in your body. They feel absolutely horrible. It is atrocious to be in there. If he cranks it fully up, some people could not stand it. And so what it tells you is that what looks really pretty and controlled and beautiful, almost philosophical by just looking at the pattern, when you undergo preheating events or parametric resonance, it is absolutely unpleasant. And so was for me a real eye-opener that the early universe was a very hostile, unpleasant place where you create a violent explosion of particles, and this you can step inside these simulations and feel it by yourself, because body is made out of fluid. And that's how I want to end. This is just a gravity laboratory group, and also colleagues like Lina and also Ulrike. Ulrike is an astronomer, but also an artist. And Alistair, who is our artist here, and also Tassos is another colleague who is doing particle physics and was also part of this program. Thank you very much.
Thank you very much, Silke and Lina. We have time just for one, two brief questions. Yeah, Jeff.
Hi, Silke.
Hi, Jeff.
Hi. I have a few questions. I'll start at the end. You mentioned you showed okay, there's the preheating, which is like the parametric resonance, but there's also reheating.
Sorry, when I said this, I have to apologize. It was the whole day in the lab. It's preheating is the onset. I'm talking about reheating. Yes.
I couldn't hear what you said. The preheating, okay, is the parametric resonance.
Reheating. Preheating is so in fact in cosmology it depends who you ask how you distinguish between the different phases. What I'm talking about is reheating.
I think you're talking about preheating and reheating. I think preheating. I think preheating is the parametric resonance. Reheating is, I guess, the particles, I guess, combining and making additional particles, something scattering of various particles, something like that.
Not quite. So yes and no, because you have this from a primary to secondary, and some people consider this to be preheating. So preheating, is it just the linear part, or is it also including the next steps? You know, you go from dominate to the next one. It depends who you ask, which you're talking to. When you ask people and you ask others about clarifying it, they say it's not so clear. Reheating would be really the long-term dynamics, right?
Yeah.
If I interchange this, I'm also very sorry about, I really mean sort of the long-term dynamics, and it has different phases, which I didn't really point out. But I don't even know where these phases exactly, where one ends and the other one starts.
Okay, so my next question, when you showed a plot of the exponential growth of these various modes, many modes, like 6, 7, here. Why do they all saturate at the same time? What's so special? Just after, like at 32 seconds, they all saturate. Why is there some special time or something?
In fact, that was our that is wonderful, because this is what we actually have an analytic equation for when this is happening. The reason why this is happening is the dominant mode is the one that's sourcing everything else. So you put energy into the dominant mode, and the dominant mode now stops. And now you could say, well, it stops because it starts feeding the other ones. But this is a log plot. And what's really happening is the dominant process is actually the one where this dominant mode interacts only with itself.
I see.
It has the highest amplitude. And what that creates, it creates an additional term in your equation of motion, which can be interpreted as a non-linear damping term. And so now the mode has become so large, it bothers itself so much, its own growth has created damping that it cannot grow anymore. And this is sort of what we actually introduced, is a reduced one-mode dynamics, where we include this self-interaction. And when this mode arrests, the others have to follow suit. And as such, we are able to predict analytically when the cascade forms.
I see.
So we have, and this is now, we were successfully applying this to other scenarios. Now we have a reduced one-mode dynamics model that makes can calculate the time needed to reach the far from equilibrium steady state. There are other reduced dynamic models. And one of them is related to this question you had at the beginning about preheating, where you have a dominant mode and you would start to scatter into the second one that grows, which is the 8-2. And there is a reduced two-mode dynamic. So you take these two modes, you have a linear theory for each, and then you have a coupling between them. And then you can also, this reduced mode can also give you a good effective description what the scattering rates into the other are. So you can now go ahead and pick and mix some things. And what we are doing, we verify in our experiments that these are precise, that these analytical reduced dynamical models have validity. So you can use simulations as this to validify these reduced dynamics models, which allow you to make prediction analytically. And this is super cool. And I think this is much more general. And we have now applied it to superfluid helium as well. And I think that there are many more systems like BSCs where you can use this and make concrete predictions what the maximum amplitude is you can reach.
Mm-hmm. Oh, very nice. My last question is, when you showed your beginning data, the blue, like on this very same graph, there's the blue waves in the experiment. The blue section of the current slide.
Yeah, this one here on the top.
Yeah, yes.
Yeah.
When you showed the movie of that, at the very beginning, there are waves like circular, like sinusoidal waves coming in from the edges, right on the edges.
Yeah. Good spotted. Good experiment. Good spot all this. It's because what you have because you know your boundaries are shaking. Okay, and they give you radial waves. So
right, are these parametric, or are they actually at the frequency of the drive?
They are at the frequency of the drive.
I see.
And the other ones are at half of the driving frequency.
Right.
And so this is the difference. We also need to check very carefully that we're not just exciting higher harmonics linearly. So this is why all the correlation measures and show that this is really a nonlinear process. So this is because this is different. In BSCs, you can actually remove boundary, kind of open boundaries with box traps and all sorts of things. You can also, creating the boundaries are easier to control in BSCs as in fluids. So here, this is actually one of the hardest things to really model right and understand right, the boundary conditions.
I see. Those are all my questions.
There's one interesting thing. I believe that there has been a bit of a mix-up and a confusion in the BSC community, because there's a lot of data where they look at wave turbulence. And if you look at this system, clearly, wave turbulence means you lose all structure, right? You have big eddies, like, all these smoke patterns that go from large to smaller and smaller and smaller. And here, you can see, even if you shake it in the highly nonlinear regime, you still have a pattern. And so, but while you have this pattern, you analyze it, the pattern still has a spectral cascade. But this is not enough to show that turbulence. You need to show more. And in weak wave turbulence, people are much more careful with this. While often, I think in BSC experiments, they just show this cascade and say, when I see this cascade, I know I have turbulence. And that is simply not true.
Okay, next speaker is Karen Crowther from the University of Oslo. The title of her talk is Dumb Holes in Universality or Analogy. Please, Karen.
Yeah, thank you. Thanks for inviting me again. So I've given this talk in Milan not so long ago. I haven't had too many new ideas since then, but a few. And for some, it's going to be new anyway. So, okay. So yeah, I'm talking about dumb holes rather than the sonic black holes. I just thought it would be cool to publish a paper with the word dumb holes in the title, but that's probably exactly why you don't refer to them as. So yeah, preference. Okay, so the big question we're interested in is, of course, are black holes hot? Do they radiate as Hawking predicted? And we don't know because we can't access the black holes under the relevant conditions to confirm whether or not they're radiating. But we can build analog black holes in the lab. So I'm here using these little bathtubs as a symbol of all the different varieties of experiments, and I hope that's not offensive. But I like the image of it. I think it's quite cute. Not to in any way undermine the technical sophistication of these different experiments. So that's the foam. Good. So can we test in the lab? And of course, we've got these actual models being built in the lab from Silke, who we just heard from. And I was very privileged to be visiting her lab to see her systems there. And we've seen from Jeff here his systems. So can we look for the Hawking radiation? And if we find Hawking radiation in the lab, does it tell us anything about black holes? Can we confirm Hawking radiation in astrophysical black holes? And so Radim, Karim, and Eric Winsberg here argued that yes, if we can, under certain conditions with our experiments in the lab, we can confirm the existence of Hawking radiation in real black holes, astrophysical black holes, I would say. And then Stephan joined in and did a Bayesian analysis showing how we can even quantify the amount of confirmation we have doing this Bayesian analysis. And then us in Geneva, so me along with Niels and Christian Wüttrich, Niels Linnemann and Christian Wüttrich, we argued no. Which started a bit of a discussion. So we had Paul Bartha also saying no. And we have Grace Field, who Lina mentioned as well, kind of, not currently. So now I thought I'd revisit, thanks to Francesco's paper with Niccolo Cagnotti as well, who's saying, well, actually, yes, we could have confirmation potentially, but not in the same way that the DTW paper was saying. So DTW and DTHW being short for the Dardashti, Winsberg, Hartmann, and Thibault papers. So they're saying yes, but for different reasons, and keep being invited to talk about analog black holes. So I thought I'll revisit this. This is a good question. What is so special about analog simulations? So I thought I'd revisit this question, being very inspired by Francesco, of course. So let's explore. What is special about analog experiments or analog simulations such that we think they're somehow different from regular experiments? Like, why are we even having these debates, asking whether they can be confirmatory or not, which we wouldn't do for regular experiments? So what makes them special? So I'm interested in particular, how do the analog black holes for Hawking radiation differ from conventional experiments? Are they analogies or are they simulations? So these are the questions that I'll be asking today. And after thinking about it a bit, I'm thinking, well, actually there's kind of nothing so special about these analog experiments. Under some conditions, they can be analogies. Under other conditions, they can be conventional experiments. I'm going to argue that they're not simulations, so that's something at least. And at the moment, I think they are analogies rather than conventional experiments. So I'll start off, I don't need to say too much about Hawking radiation and the analog models we've heard from Jeff already. And then asking this question, what is an analog experiment? And then there's kind of two different ways in which we can approach this based on the papers exploring how they can be confirmatory. Are they confirmatory by universality, which treats our experimental system and its target as being of the same type of system? Or are they better thought of as being different types of systems that are just analogous to one another? I'll then consider whether they're both. And if I have time, I'll say a bit about whether they're simulations or not. But then what is special about the particular case of the Hawking radiation? Okay, so Hawking radiation, I'm not going to go over it in much detail, we've heard it already, but just to emphasize that to get a full explanation of black holes, we need the theory of quantum gravity. We don't have this, but we're seeking to anticipate its results using our approximations of QFT in curved spacetime. This is a non-trivial framework that's combining both general relativity and quantum field theory. It's neglecting back reaction here. And this framework is not well confirmed itself. So the evidence we have that this theory even works at all is very highly indirect and not specific. And I won't go over the details over this. You can see our original paper there. So in particular, we don't know whether it applies at all. And secondly, we don't know the conditions under which this framework is going to be a good approximation to quantum gravity. But one thing we can expect is that it's not going to be a good approximation in the Planck regime, because this is where we need the full theory of quantum gravity. So Hawking, of course, uses this framework to predict the Hawking radiation, which we can't detect in astrophysical black holes for exactly the reasons Jeff said. When they're very, very big, the radiation is very, very small, many million times smaller than the cosmic microwave background radiation. So we can't really, it doesn't look like we're going to be able to detect it. Another problem with this prediction, again, which Jeff mentioned, is this trans-Planckian problem, where this calculation is predicting that the field modes emitted, when we're tracing them back towards the horizon, they're going to get very, very high energy, and it's going to go into the Planck scale, which is where we know this approximation is not going to hold. So it's a bit of a self-consistency issue, because you've done the approximation assuming that we can neglect these quantum effects, and now you're going into the quantum regime, quantum gravity regime. So it seems to undermine the reliability of our derivation. So what we want to show, if we want to show that our predictions are still reliable as an approximation to quantum gravity in the non-Planckian regimes, what we want to do first is to demonstrate that whatever this high energy, unknown quantum gravity microphysics is, it's not going to affect the appearance of the radiation. And as you said, you've got one step towards this as well, by showing that we have microphysics and it's not affecting the appearance of the radiation in this case. So in other words, we want to show that Hawking radiation is robust to the microphysics. Whatever is going on, it's not going to affect the appearance of the phenomenon. So yeah, I couldn't resist putting in this picture as well because it's just so cute. UNRWA, of course, proposes these dumb hole models, the analog black holes with water. The waterfall, Jonas, because you missed it, it's a waterfall. And these are little fish. One fish has gone off the edge of the waterfall, and we're supposing that at this point here, the speed of sound, it's slower than the speed of the water coming down. So it means that no matter how much this fish is screaming, help me, to his friend up here, the sound waves cannot get past this horizon. So you have this sonic horizon here, analogous to the black hole horizon where light can't escape. Here we have it that sound can't escape. And yeah, that's also why they're called dumb holes, because they're mute. They can't speak to us, like being deaf and dumb. And the fish have ears, so they can't hear each other. So we build these systems. Well, here's the theoretical proposal by UNRWA. And what he showed was that given a certain setup, I won't go over, we can set these up where the configuration of our system, the background, is directly analogous, isomorphic to the one we use to describe Schwarzschild black holes. Okay. So yeah, basically you can see here, now we want to demonstrate based on the concrete realizations of these different models in the lab, no longer just being the analogy on paper. We want to show that when we do different experiments with different microphysics, we're going to demonstrate the existence of the phenomenon. So we want to show that the effect is universal experimentally, as well as showing it theoretically. Okay, so what is an analog experiment? So here, generally, for any case of experiment, we talk about an experiment being internally valid when it's probative of the particular system right in front of you in your lab. That's your source system. If your experiment is telling you about that particular system that you're doing the experiment on, then it's internally valid. And then an externally valid experiment is one that's probative of a different system. Any other system, supposed to be in the more general class of systems that the one you're experimenting on, your source, is supposed to represent. So those are your target systems. And of course, your source and target are supposed to have in common some particular salient properties. They have these shared features, which are the ones that are interesting for you. They're the ones relevant for the phenomena you're investigating. So for an analog experiment, we can see in the dumb hole case that we have the water being analogous to space-time, and then the salient properties in our source system being the speed of sound, the velocity of water, which are analogous to the speed of light and the curvature of space-time. And as briefly flashed up, they can be described by formally similar equations. So then it seems like we're using analogical reasoning. So here you can see this is standard reasoning by analogy in science, where we recognize that our source system is similar to our target system in certain known respects. And then you see that your source system has some further feature Q. And from the analogy, you infer that your target also has the feature Q, or some feature Q star, which is similar to Q. So this form of reasoning is inductive rather than deductive. And for this reason, is not typically thought to be able to provide confirmation. Like you think of the Galileo case, or just a direct analogy between kind of, oh, there's water on Earth and it's round. Maybe there's water on Mars and it's round. Therefore, there's life on Earth and life on Mars, something like this. It might give you a reason to investigate and do more experiments to find out, but it doesn't tell you, doesn't give you confirmation of what it is that you're trying to infer here, this feature Q. But yeah, it can give you heuristic plausibility. So in the DTW paper, this is the definition of the analog experiment, and it's also their way of arguing that we can get confirmation from these analog experiments. You have the modeling framework S, which is describing your source system. Secondly, you have a modeling framework T, which is describing your target system. You observe that MS and MT are structurally similar, syntactically isomorphic. You want to know something about your target system, but you can't observe it under the relevant conditions to find out. But you can do so for your source system. You see that it exhibits some phenomenon PS. And then from these formal similarities in 3, being the analogy here, so this is the analogy step, you infer that your target system also exhibits phenomenon or analogous phenomenon PT. So you can see here in DTW, they're utilizing analogical reasoning, but they don't think analogical reasoning alone can give us confirmation, but they are arguing that analog experiments can give us confirmation. So somehow this is supposed to be stronger than just analogy, something different than just analogy. So what we're interested in is, well, how do we distinguish between analog experiments and conventional experiments? A first obvious kind of stab at this might be to say that in conventional experiments, your target is supposed to be of the same type. So for the purposes of the investigation, it's the same type of system as your source system. Whereas in analog experiments, they're not supposed to be the same type of system, but just analogous to one another. So the salient properties that you're interested in are not exactly the same ones, but just similar to one another. This, though, doesn't work because what it is to be the same type of system for a specific application in physics just is to have the formally similar modeling frameworks. If they're both described by the same equations, then it's the same type of system. It doesn't matter if one is made of cheese or one is made of rock. They are the same type of system if, under those conditions you're interested in, they're able to be described by the same equation. So an example here, of course, being phase transitions, such as like you can think of ferromagnetism and domain formation. Here we can see in phase transitions that we get the same sort of behavior in systems of very different constitutions, fluids, metals, or even the universe itself. And these systems can all be described by formally similar modeling frameworks. So if we're just interested in the phenomena of phase transitions, these are the same type of system. So anything they have in common or any differences they have between them that are irrelevant to the behavior phenomena you're interested in are just not salient. Another example, so we say that the systems being described by the same equations, the same modeling framework, that they're falling within the same universality class. So using this quite broadly here, not just for the specific kind of RG analysis, but broadly, that's what I mean by universality class. Another example, if you're interested in resonance in a pendulum, in this case, you can treat a mass on a string as the same type of system as your LC circuit. So they look like they're very different types of systems, but they're both exemplifying the relevant behavior of interest, and they're both able to be described by the same modeling frameworks that are syntactically isomorphic to one another. So the idea is that even though they look very different, they have different constitutions, when we move to some higher level of abstraction, you can treat them as being of the same type of system, being within the same universality class. In this case, they're both simple harmonic oscillators. So again, as I said, moving to some higher level of abstraction, the systems are in the same universality class as defined by your modeling framework. So in this case, once we've moved up and identifying these two different compositionally systems, At some higher level, they're of the same type, and this shared behavior that we're interested in is said to be universal, and then the systems that are exemplifying it are then within the same universality class. And we can see then for any externally valid experiment, your source system and your target system need to be relevantly the same type of system for the purposes you're interested in, which means they're both described by the same or syntactically isomorphic modeling framework. They're exhibiting relevantly similar behavior. So you can think like an example that's not a physics example being a lab rat in the drug trials. In this case, the rat isn't an analogy for human beings, because that would be that they're different types of system. Rather, we've moved to a higher, more general kind of level of abstraction where we are both mammals, humans and the rat are both mammals, so we are relevantly the same type of system here. And this sort of argument with the universality is what DTW are looking for when they're arguing the confirmatory nature of the analog experiments in the dumb hole case. They want to show that the dumb holes in our lab are in the same universality class, the same type of system as the astrophysical black holes. And thus we would have a conventional experiment. And I really liked this picture. It's not mine. You can see the authors here. We now have, many different systems in the labs. We've got the astrophysical ones not in the labs. But we have aquatic Hawking radiation. We have sonic Hawking radiation, optical Hawking radiation. And these authors are arguing that, well, it's not that one's aquatic Hawking radiation, one's sonic Hawking radiation, that they're different types of phenomena. Rather, they're just all the same type of phenomena. It's all Hawking radiation. And in this case, they're all the same type of system, even though they look very different. So then on this reading, well, what distinguishes an analog experiment from a conventional experiment? It would seem like there isn't a difference. On this universality reading, it's not that they're supposed to be, the dumb holes are analogous to black holes. They are black holes. They're all black holes. So they are, for the purposes of investigating Hawking radiation, the same type of system. So what makes this case special? It seems more like it's just a conventional experiment. So why are we calling it an analog experiment instead of just experiment? So this is why, me and Niels and Chris argued, well, we can't see the difference here. What is the difference? Based on the DTW and the DTHW argument, it seems that the answer must be in the inaccessibility of the target system. In regular cases of experiment, we know enough about our target system that we know that they are the same type. But in this particular case with Hawking radiation, we have extreme inaccessibility of the black holes. So maybe to be an analog experiment just means that we can't access the target system to know whether or not it's in the same universality class. So that's what we argue, that we just can't access our target system in these cases. And so we don't know whether they're in the same universality class. And this had the implication that the external validity of an analog experiment is just unable to be determined, kind of by definition. So even though the dumb holes in our lab are described by this modeling framework MS, which is syntactically isomorphic to MT, the framework which we believe describes black holes, we can't actually say that they're the same type of system. Okay, but now after being invited to reflect on it a bit more, and papers that have been published since, or at least written since, I've changed my mind. I no longer think that it's about the inaccessibility. So it's not the inaccessibility that makes these experiments special. Why? Because, yeah, what's happened is that people don't seem to like the implication that analog experiments can't yield confirmation by definition. This is maybe a bit harsh, because, like, yeah, since we can't get the external validity there, we just can't learn anything about confirmation. We can't get confirmation from any analog experiments. So maybe that was a bit harsh. We can rethink it. And other responses point out that there are plenty of other cases where we're doing experiments which we do have inaccessible target systems for, such as, dark side of the moon or stellar nuclear synthesis. And we can get confirmation in those cases. So it can't be the inaccessibility that's ruling out confirmation, or that it's special in defining analog experiments. So revisiting this, I think in general, they shouldn't be defined by inaccessibility. But I think for the Hawking radiation case, inaccessibility is still a problem for confirmation. So on the universality reading, what's special about analog experiments? I've said nothing. If we're going for universality and saying that they're the same type of system, then we should just call them experiments rather than analog experiments. What about the analogy reading? So, yes, Nappo and Cagnotti here have proposed an alternative reading of the dumbhole case, arguing that they are material analogies, material in the sense that have been concretely realized, but also using Hesse's definition of material analogy here. It doesn't require, very importantly, it doesn't require that they be the same stuff, like they're not materially similar at all. But basically, the thought is that in drawing inferences from the dumbholes to the black holes, astrophysical black holes, we're just employing regular analog reasoning. And then on this reading, yeah, scientists employ reasoning by analogy all the time. And then it doesn't seem like there's something special about the analog experiment case either. Okay, so it seems like so far there's different ways of reading these experiments, but maybe nothing that makes the title analog experiment kind of necessary, right? Unless all we mean is that it's on the analogy reading, that it's an analogy, no longer just in the journal articles or on your blackboard, you've actually concretely built it in the lab. So it's a material experiment that you're experimenting on, and it's an analogy. Okay, so it seems that maybe it's not so unusual. And the idea is that maybe, well, we can have both. I always put this in, and I'm not sure it means anything to anyone, but it was this ad on TV back in Australia when I was growing up, where there's this family having a fight over tacos. Do we want soft tacos? No, we want crunchy tacos. And then they're fighting, and this little girl pops up like, why don't we have both? And then everyone cheers. So they think this is the way to go. We can have both. And say exactly this: an analog experiment is best used to refer simply to any experimental, meaning accessible, manipulable system that you're taking to be analogous to your target system, which on the new reading need not be inaccessible nor unmanipulable. And I had this revelation, of course, and then I found, oh, hang on, I'll come back to this. I think on this, you can see that I think any experiment is an analog experiment, right? Because we're always, oh man, I've got my slides messed up. Anyway, so I'll just go with what's on these slides and come back in case I miss them. But I think basically, yes, we can treat any experiment as an analog experiment because we're always using analogies, right? You know, when you're doing your setup in the lab one day, and then the next day you come in and you reset it up. So it sounds like you just leave it running.
Yeah, I can't turn it off.
Yeah.
It takes me, I leave it off for a few months.
Yeah.
It takes me half a year to a year to get it working.
Oh, boy. Okay.
It's off right now. It's not one of the experiments it's going to cost me.
Oh, the power back on. Okay. So say we want to run the experiment again in half a year. You're still relying on an analogy between your original setup and the new setup, right? It's not the same system anymore because of the temporal distance. Yeah. Like you today are not the same person you were yesterday, but you're analogous to them. This is what we do in philosophy. So I think in all cases of experiment, we are using analogy. But when we do want to draw a distinction between conventional experiments, which also utilize analogy, and analog experiments, I think we can just use these labels, or definitions, sorry. In a conventional experiment, we say that the source system is known to be of the same type as its target for the purposes of the investigation. Whereas in an analog experiment, the source system is not known to be of the same type, meaning we don't know whether or not it's the same type, or perhaps we know that it's not the same type of system, but they are both analogous to one another. So those are the definitions I'm proposing now, so that we have a distinction between conventional experiments and analog experiments without relying on the inaccessibility anymore. Inaccessibility is no longer in the definition. Okay, so the idea is that for the dumb hole experiments, now they are analog experiments in this sense, they're analogies. We don't know whether or not they actually, the black holes and the dumb holes are the same type of system, but we know they're analogous to one another. But the idea is that once we get more information, such that we're able to infer that they are the same type of system, then your experiment can be upgraded to being a conventional experiment. It's no longer just an analogy, they are the same type of system. So it changes depending on how much information you have. Once it's externally validated, your analog experiment gets upgraded to just being a regular experiment. And yeah, as I was trying to say before, I was thinking about this and then I found that other people already had a similar idea where, so it's Hangleiter, Caroline and Thébault talking about analog quantum emulations, very nice book dealing with many different types of experiments, and they're getting a more general framework. And they're arguing that these analog quantum emulations, when they're unvalidated, they're functioning like material analogies, meaning they can give us how possibly understanding, so how possibly could be mechanisms. And once they are externally validated, they function in the same way as regular experiments, giving us how actually understanding. So I'm agreeing with this in the case of the Hawking radiation case as well, and in the case of analog experiments generally. So again, I think on this reading, there's nothing special about analog experiments either. They're analogies, So when they're not externally validated, when we don't know if the target is relevantly the same type of system as our source for the purposes of the investigation, or where we know that it is in fact not relevantly the same type for our purpose of the investigation, but it's still useful to do an experiment even though they're not the same type of system. For instance, when you have like ethical considerations or monetary financial considerations, it still can be interesting to do an experiment on systems that are not known to be of the same type but are analogous to one another. And then they can get upgraded to being conventional experiments once we get enough information to confirm that they are relevantly the same type. Okay. And as I mentioned, I think all experiments are analogous, as I just said. One of the reviewers gave me this analogy, that just as an airline passenger who gets upgraded to first class is still an airline passenger, so the conventional experiments are like a subclass of analog experiments. Okay, so then what's special about the case of the Hawking radiation? It's the inaccessibility. It's extreme inaccessibility here. So we can't relevantly access the black holes in the conditions that are required to confirm whether or not they have Hawking radiation. So we can't establish the external validity of our experiment. And I think this is different from other cases of inaccessibility in science, where we can do experiments to learn about inaccessible systems. But in this case, the inaccessibility is so extreme that we don't have the external validation. But it's possible that we can get external validation. So how do we get this case closer to other examples of conventional experiments on inaccessible systems? I would say, yeah, we need some independent tests of QFT in curved spacetime if we can figure out that it applies. Or perhaps if something unexpected happens in the dumbhole experiment, like a prediction, and then we could test that, then that could be a way of providing external validation. So it's possible. So at the moment, they're not conventional experiments, they are analogies. But even though they're unvalidated, they can't give us confirmation of Hawking radiation, we can still learn a lot from them. They're very powerful heuristic tools. We can explore different possible mechanisms of the Hawking radiation effect, explore intuitions, and provide understandings. But yeah, all of this kind of presupposes, if you're wanting to learn about black holes, that the effect actually applies in black holes. Otherwise, I like the way you said it, we're learning about the theory, we're confirming the theory, or we're learning about the particular setup that you're working on, your source system, or the different stamps, but not including the astrophysical black holes. So if I have time, I'll just comment on simulation. Are analog experiments better thought of as computer simulations or analogous to computer simulations? And I found this paper by Rush was very interesting, where she's arguing that, as Winsberg also argues, that for simulations, the person doing the simulation needs to make a model of the target system, but in the experiment, we don't have to, which sounds like it would put the dumbhole case more as a simulation, because we are making a model, and in fact, we can think of the experiment itself as being a model. But what's interesting is that they're arguing that the simulator needs to make more specific commitments about the unknown structure and dynamics of the world than the experimentalist does. So basically, the experimentalist is working on an actual piece of the world, whereas and has all these unknown physics built into it, whereas the simulator doesn't have that. They just have to kind of guess when they're building the model what are kind of the unknowns here that could affect it. So the idea is that simulations and experiments differ with respect to the unknowns. Neither the experimenter nor the simulator has knowledge of the unknown matters that might affect their results, but at least the experimenter will witness the consequences of this in their results, because the unknowns are there in the world. They're coming out in the experiment, but they're not there in the simulation. You haven't built them in. You don't know what could come, what could affect it. So in this case, experiments are superior to simulations in those cases where there are elements in the experimenter's source system that will affect the results and are unknown. And hopefully you can see now that I think the dumbhole case comes out as an experiment here. Because it's not like the artificiality. I was thinking about the artificiality, like in the dumbholes, we're setting them up in such a way that they will precisely instantiate these equations, right? So it seems similar to a simulation because that's what we're doing. But then in these dumbhole experiments, the microphysics is there automatically, right? So the idea is that multiple different experiments on systems with different material constitutions are going to demonstrate this robustness with regards to the microphysics. And the aim of doing all these different experiments, as Stephan pointed out, is to precisely show that these unknowns will not be relevant to the effect in the target systems, as you said, the quantum gravity, microphysics. So I think this account is quite nice because it shows clearly that dumbholes come out as experiments rather than simulations. Good. Okay, so that's it. In summary, I'd say that in analog experiments, we have our source system analogous to our target system, and we don't know whether or not they are the same type of system for our purposes. But also there might be cases where we're running it and we know that they're not the same type of system for our purposes, but they are analogous to one another. And as analog experiments are analogies, they can't yield confirmation of hypotheses about your target system. Whereas in a conventional experiment, you've got S and T being relevantly the same type of system. There's still analogy being used there, but now you've been upgraded. And now they're capable of confirmation. But at this stage, the dumbhole experiments for Hawking radiation are analog experiments because we don't know whether or not the lab setup is the same type of system as the astrophysical black holes. But if we do, as I've suggested, get some indications or other lines of evidence for thinking that QFT in curved spacetime applies to actual black holes, that it is a good approximation to quantum gravity in the regimes we want, then the dumbholes can be upgraded. And finally, I've argued that they're better off thought of as experiments rather than simulations. So thank you.
Thank you, Karen. Question, Vincenzo?
Thank you very much, Karen, for your wonderful slides and very amusing and interesting and stimulating conference. I have a question. You said at a certain point that we all agree that analogical reasoning play a certain role in the discovery and make something plausible in the sense that we look for that kind of feature or peculiarity because our analogical reasoning between the target and the source point in that direction. Okay, so this means that in a sense even if this kind of role is in the discovery, analogical reasoning, a bit of capability as justification should have a bit of this kind of, not a big one. Coming back to the case of the Hawking radiation, indeed, we know all physicists believe in the existence of Hawking radiation, not for experimental ground, but because there are many different kind of models that arrive at the same conclusion, so that in a sense now is considered by people working in this field as a sort of theoretical evidence. Yes.
Of course.
To speak of confirmation is enough that relative confirmation is enough that this kind of experiment increase a bit.
Yeah.
It is difficult to say that it is not.
Yeah. I know what you mean. Like we've explored all the different possible conditions under which these equations could break down, meaning that the phenomenon doesn't get exemplified, all these different types of microphysics. So don't we then have reason to think that, whatever is going on in quantum gravity, our equations are robust enough that it should still hold? And I think quantum gravity is just so far and so unknown. Like, we're talking about many, many orders of magnitude. It could be a complete new scientific revolution. It might be completely different type of physics than we could even imagine. Something completely different to atoms in the lab. So yeah, I think in this case it's just too far unknown.
Okay, if there are no other questions, I think that we can close the conference. Thank again to Karen and all the other speakers of today, and also the public.